Okay, so Ampere's law, you could actually show that if I'm putting a current through my wire and my compasses will come out, and you can see that I'm generating a magnetic field. So we know that an electric field will generate a magnetic field. So that was one of the interesting observations that we had. And then one of the things that we saw is with our solenoid, I could make an electromagnet and I could have a uniform magnetic field inside my solenoid. So I could get that. So the question became, well, if an electric field produced a magnetic field, would it go backwards? Would I get something else? And so what Faraday did is he created an iron ring and he put a coil around the iron ring here. And then he put another coil around the iron ring here. And when he put a current through this, so we got a current going in there, when he flipped the switch of the current, you actually saw a current show up on this side. And that became the first indication that I could get the magnetic field was going to do something that actually would cause the electric field. So this gave you the reverse being true. The other thing that was interesting is if you take a wire and you make a loop of that wire and you take a bar magnet, and we know that it has its magnetic field off of its bar magnet. If I move this magnetic field through a loop, I'm going to actually generate a current. Now, the key here is this has to be a changing magnetic field. And that's an interesting observation. It had to be a changing magnetic field because once I had a steady state current in here, this didn't do anything. It had to be a changing magnetic current. So this gets us to this idea of flux again. Now remember, with my Gaussian flux, if I had my charge inside my item, I had it go through, and my curve surface here was giving me my flux that was going through the surface. But for my magnetic field, it's a little easier because I can take a square loop and I can look at my magnetic field or my field going through my square loop here. And we can define my magnetic flux as the maximum, of course, is when the magnetic field is perpendicular to the area. And this is going to give me my maximum. Now, as I move my field, so now I have my plane here, and I go through my field, this is going to have a flux of 0. And anywhere in between, my magnetic flux is going to be based off of my BA cosine of my angle, because that's how my flux is going to change. And these are in units of Webers, and it's a WB, and that's what you get for Webers. Now, the idea here, and what my idea about magnetic flux, it becomes very important when I'm dealing with AC circuits, because what's happening with an AC circuit is always changing. So if I'm running AC through here, this is always changing. I'm always going to get something that's happening with my magnetic field. And that's really what we have to worry about when we're dealing with this time dependence. And this is one of those things that we end up with dealing with a little bit differently than what we have. So we get this idea that we get the flux and Faraday's law. Now, interesting thing about Faraday. Faraday was actually an experimentalist for the Royal Society. He actually didn't do the mathematics, other people did the mathematics, but Faraday's law says if a circuit contains n loops, the magnetic flux through each loop changes, and we do the delta this during a time interval. Delta t. Now, so this gives me my EMF. This is my EMF induced is going to equal a negative in change of this. And this negative is giving us the direction of the current. And that comes from Lenz's law. And this says that the current caused by the induced EMF travels in the direction that creates a magnetic field with a flux opposing the change in the original flux. So what this is saying is, as I am changing my magnetic field, Lenz's law says we're going to try and oppose a change. Essentially, if I'm going to have an AC circuit and I put an inductor in it, which is a device that's going to be able to store energy, and it's a device that helps my circuit, it's going to resist the changing of the circuit. It's going to try and keep the circuit steady. And how this is observed, so let's say I have a pipe, and one of the videos that you see out there is this pipe. And if I drop a ball through the pipe, so this is just a steel ball bearing, it's going to fall and it's going to do, we're going to get our change in energy, right? We get our change in energy and we go, our potential energy was going to be mgh, and at the bottom it's all kinetic energy, which is 1/2 mv squared, and we can see that the force that's being pulled down is our force due to gravity. So if I just have a ball bearing, and this is just a basic ball bearing, now let's say I have a magnet. So my magnet is going to be a little magnet, and we're going to give it a north and south pole. And we're going to drop it down a conductive pipe. Now, what happens in my conductive pipe is it's going to look like a whole bunch of individual little wires, right? They just happen to be spaced closely together. So if this has a magnetic field on it, what's going to happen is as this goes, and I look at my force diagram, I have a force on my object that's due to gravity. This is my force due to gravity, but I'm going to have a magnetic force that's opposing it, because what's happening according to Lenz's law is as I drop this through, the current is going to create the direction of the current is going to try to repel this particular magnet. And so because of this, I'm not going to, my ball is going to take a lot longer to fall through this tube than just my regular ball bearing, because I have an opposing force that's causing a drag on that particular object. And it's all the result of the opposing magnetic field that the current is bringing about. So I get this really interesting piece of it. So that helps you find your direction of the current. Now, lucky for us, you know, as we do, when you guys get your quiz on magnetism, it's going to be more conceptual rather than problem solving, but we will actually get it in there. But that's the idea of finding the current. So if I have a wire here and I have current going into the wire, and we know what that's going to happen is I'm going to put my thumb in here. I'm going to get a magnetic field that's going in there into the page. So if I get this magnetic field into the page, it's going to want to create a current, and then my current is going to go the other direction. So you can actually work through these things by playing with Lenz's law. Now, the trick about all of this comes into play as when we start dealing with AC circuits, we're going to have that working. So now let's look at the force max due to my electric field and my force max due to my magnetic field. This, remember, was Q times my magnitude of my electric field. And this is QV times my magnetic field. I've got my charges are the same, but the key here is this has a time dependence. But you can see that they're related, and that is a really cool thing. So if I do the magnitude of my electromotive force, that's going to be, if I'm doing one loop, so let's take a diagram here. I'm going to put a resistor into my system just to make it work easier. I have my electric field going in here, and I have a conductive bar, so I only have the one loop, and this is separated by a distance L. I can measure, so I've got all this going in here. And if I put current into the system, this bar is going to move. And it's going to move. My change in potential is going to be E times L. And that's BLV, so that you get that. My flux is B times A. And if I do this, this is my area, so this is X. Well, we're going to do this as a Y, just to make it clear that I'm not dealing with my magnetic field. So area is going to be L times Y. That's my area times my magnetic field. And if I do a change here, and this can be a change in Y, because if this is moving, I get a change in Y. And now if I do my electromotive force, there's my flux divided by my change in time. So now I get LB change in y over change in time. This is my velocity. So we get that velocity and we can play with that. And this is what they call a motional EMF. Now, for most of you, you're going to run into this in terms of instrumentation. Okay. This is how we make things like amplifiers work on a electric guitar. There are certain medical pieces of equipment that use this to help you out. But the big thing here is it gives us this idea of an inductor. And I'm going to switch over here for inductor. Oh, there's my inductor. All right. That if I have a device in my circuit that we draw like this, what's going to happen is when I open and close my circuit, this device is going to store energy. And if we come back to this idea here, where as I am moving something, but this is now fixed, it can't move. We talk about an EMF, which is going to be like our potential. And this is going to equal, we give it a negative L times the change in my current over my change in time. And L is called inductance. And inductance is going to be kind of like capacitance. It's going to have units of henries. And we can actually use these things and they become important in our AC circuits. It's going to have a time dependence. It's got a time dependence. So just like if I remember when we did RC circuits, I can do RL circuits. But my time dependence for an RL circuit is going to be L over R. But it's going to charge or it's going to hold energy just like my capacitor does. So these hold energy just like your capacitors do. They have power associated with them. We can do calculations with them very much like what we've done before, except this now has a timed dependence on it. That's just a little bit different. And the energy stored in an inductor is equal to 1/2 the inductance times the current squared. And if you want to compare that with the energy in a capacitor, that was 1/2 my capacitance times my change in potential squared. So those problems work very similar to what we have. Now, what I'm going to do tomorrow is we'll talk about generators tomorrow. And we will review generators and looking at it. We've already kind of done that already. We talked a little bit about it yesterday, but that covers the material that we have in terms of magnetism. And then what we're going to start with next is we're going to look at alternating current and this idea that magnetic fields and electric fields are tied together. And that's going to be a key item as we get to light. So questions?